Well, hi everyone, and thank you for joining in another joint information session hosted by All Control and SICK. My name is Sydney King, and I'm actually one of the application engineers at All Control and the SICK specialist here. Actually, on this call, I believe we're also joined by Jim Stanowiski, who's a director of engineering and sales, also an application engineer here, a lead engineer actually, and Kevin Gilbert also, who's also another application engineer, and the sales guys that are also part of this call. Today, we have SICK safety application specialist Sean Kellen with us, who will be discussing the SICK 3D vision sensor, the TriSpector actually. This is an easy to use and program 3D vision solution that is well suited for a lot of applications out there in the past that we had thought were pretty much challenging and expensive. And the SICK 3D TriSpector actually is a perfect solution for some of these applications. For those of you who are not actually or who are unfamiliar with SICK, they are a manufacturer specializing in sensor intelligence, basically including vision inspection, sensing, and automatic identification and safety sensing technologies used all over the world in manufacturing and industries throughout the world. Basically, All Control is basically All Control is a local technical resource. We're the distributor for SICK, actually an elite distributor, and we've represented SICK for the past 30 years. For those who you are not aware of that, we have a group of sales and application engineers, like I mentioned earlier, and we're locally available to assist you with any of your automation application needs. If there's anything we can talk about today that you'd like to see in person or discuss, let us know. We can come out to your facility, or you can come out to our office. We're located out of Elgin, Illinois. We have a large inventory of products here at the office to demonstrate and show you, including the TriSpector, which is the topic of discussion today, and many other products we can test out at your facility. Our goal this morning, actually, these are just information sessions, so we can offer value to our customers by getting the word out on new products that are coming out and technologies out there that are available to us. So keep in mind, we're not pro web cameras out there or anything like that. It's not some big budget production or anything like that. So feel free to ask us any questions you might have, comments or thoughts as this session is going through, and we can kind of answer as we go along or towards the end. Also, for all of you that actually signed up, we have a gift for you guys. You'll be in a drawing. We'll notify you days or weeks ahead for the drawing that you guys all signed up for as well. So thank you so much for taking the time today and joining us. We know you could be anywhere else right now. So without taking up too much time, I'd like to introduce Sean Callan, who will explain more and talk about the SICK 3D vision inspection TriSpector. Take it away, Sean.
All right. Hey, everyone. So my name is Sean Kellen. I work for SICK Sensor Intelligence. I'm based out of Minneapolis, Minnesota here. So switch the screens on me. Let's do it like this. Sorry, 1 second here. I'll share the other screen. There we go. So like Sydney said, I am the vision application specialist based out of Minnesota. So today we're going to talk about the TriSpector, which is one of our 3D vision cameras. Just as a quick note of what else I cover in the Midwest region here, basically anything from SICK that outputs data. So that could be single point distance measurement devices, positioning with 2D or 3D cameras. I also cover the LiDAR devices, which could be generally AGVs or sort of anywhere you might have more than one sensor. We can put on a LiDAR device to cover a full field of view. Anything that takes measurements, and then also our auto ID portfolio from laser scanning devices, camera-based or RFID devices. So SICK comes at vision in 4 ways. The first way we do it is very application-specific devices. So this could be a device, could be one of our TriSpectors, for instance. So this little guy here, oh, the background wants to block it out. Could be one of our little guys here. And what we do is very application specific software on that device. So the best example I have is our 3D belt pick, which is 3D belt picking. So it is only doing belt picking. It's designed to be very simple to set up and easy to use. And all in total, on the vision side of things, takes about 10 minutes to get going when you know what you're doing here. The next step is our configurable devices. So these are cameras that have a set tools built into them in the 2D and 3D vision. And again, designed to be easy to use, click and point and drag. And that's what I'm going to be demoing today is this TriSpector 1000 configurable device. Getting a little more advanced is our programmable devices. And with these, we have a programming environment called AppSpace. And you can actually take a device just like any of these other TriSpectors. It'll be totally blank, and you can create the tools that you need to make your application work. So the benefit here is I don't have maybe some of the overhead from some of my other tools. I can maybe do things slightly more efficiently because I don't have to worry about how I'm grabbing the image as much. And so we're really targeting, you know, more advanced applications for these devices that a simple tool set won't handle. And then we also have streaming devices. And with these, we would stream to an IPC, and then you can handle that data in whatever vision library that you're comfortable with. These can also be streamed back into what we call SIM devices, which is basically a SICK IPC, and then we can program in app spaces as well. So we do cover a whole variety from simple applications to the more advanced applications for whatever you might have. So I'm going to start diving into the TriSpector. Right off the bat, you know, why is the TriSpector, why are we talking about it today? It's a 3D device, it's configurable, it's standalone, everything's running on the TriSpector, it's easy to use. We've been seeing a big push for TriSpectors, especially lately, just because it's becoming easier and automation is starting to blow up. So looking at the TriSpector itself, all of the image analysis is done inside of the TriSpector. So we configure it on our laptops, then we can set it up on over our conveyor, and it's going to do everything there. We have our built-in encoder interface. So looking at the device itself, we have a dedicated encoder plug, gigabit Ethernet, and then our Power I/O plug. We also have the option for glass or plastic front windows for those food applications where glass isn't acceptable. And these can actually be changed out as well. Both of these windows for the laser and for the camera, just in case something were to happen. So this is a nice rugged housing. You can drop these and they should be okay. They get beat up quite a bit. And the only thing that you might need to replace is the windows here if they get smashed. Sorry, also IP67. And we also do have a housing that we sell for IP69K stainless steel for those applications that need it. So we have 3 types of TriSpectors, and regardless of the TriSpector, the price is the same. So one price for each one of these. So the difference between these is the field of view, and this affects our resolution. So we have our high resolution small field of view camera called the TriSpector 1008. We have the TriSpector 1030, maximum 330 millimeter field of view at the bottom. And then we have our big TriSpector, the TriSpector 1060, with the 650 millimeter field of view. So for today, we're going to look at this TriSpector 1030. That's the one I'll be demoing. And it really just comes down to how wide is, my belt, how big is the object that I'm looking at, and what do I actually need to do. So we'll get into a little more application specific things later. But generally for big belts, I'm looking at the TriSpector 1060. Small electronics, I'm looking at the TriSpector 1008. And then things that are a little too big for this, we're looking at the TriSpector 1030. So if we look at 2D vision versus 3D vision, or more specifically 3D laser triangulation, which is what the TriSpector is using. 2D vision, we're just taking a snapshot. Nothing has to be moving. And then we do, our image processing is pretty simple. We just look at the contrast on our imager. 3D laser triangulation animation. So we're outputting a 3D point cloud to the TriSpector, and we're looking at actual height differences versus contrast differences. The benefit here on laser triangulation is I don't need any external lighting. I'm using the laser that's built into the TriSpector, and therefore I don't care about contrast or having a black object on a black target, on a black belt. So just the functional principle, just so everybody is aware, we have 3D triangulation distance sensors. So it's actually, being lasers coming out, it's hitting the object, and where it hits on this sensor determines the actual height. So the same concept is now applied to this 2D receiver here. And then as the object moves closer, it's a different spot, and we get a different height. And now we just take a bunch of these profiles and put them together into a 3D image. So one more animation here for you. We can see this move. So the laser line pops up. I know the height is different. And I put that together into a 3D point cloud. So one more time, just so everybody, oops, one too far. There we go. So we project our laser line, and this camera here is a different one of our streaming cameras that we have. But it highlights how we get some of our distance values and height values here. So we project our laser line based on the angle between the camera and our laser is how we determine the actual height accuracy of the setup. We move our object in this direction, and in this case, we want very accurate measurements. So we use an encoder to make sure our object looks correct. We take all of these profiles and put them together to make a 3D point cloud. So our laser comes out of our device, but there is not necessarily, we're seeing everything that the laser could hit, because we can get too close. There's this angle of what the camera can actually see. So we have our guaranteed field of view, which would be this, maximum field of view here, the blue box. And then we can actually select and reduce that field of view, so we're only looking at the data that's interesting to us. So this is a little more in depth than we probably need here, but when we're talking about our camera TriSpectors here, we talk about our X resolution. So, oops, click, I didn't mean to. So what is our resolution across the width of the belt? Y resolution is our direction of motion, which is more determined by our encoder than our the actual camera itself. And then our Z resolution, which is the height. And this is determined by that angle between the laser and the camera. So we can see here for our various our 3 TriSpector models, our specs for these devices. So this maximum scan rate is just based on how quickly the TriSpector can actually capture our images and process. And if we shrink our field of view, we can get slightly higher than this 2000 hertz as well. So you can see our large TriSpector at the bottom of the field of view has roughly 670 micron accuracy versus our small TriSpector at the bottom of that field of view is 20 microns, and that's in the height direction. So a couple things to keep in mind with laser triangulation. There are some downfalls, because there's downfalls to everything, right? So one of those things is camera occlusion. So we might not be able to see an object behind the laser behind an object. So if we have very tall objects and we're trying to see what's behind it, we can't see that because the laser isn't visible to the camera. Likewise, we could have laser occlusion where the laser is hitting the side here, and so there's just a blank space where we can't see it. And how that shows up in the TriSpector is just no data. So there's ways around that. Sometimes just moving farther away from your object is going to let you see into these gaps here. Sometimes you just need to rotate your camera around so that you can actually see the feature that you're looking for. And that just shows missing data. Okay. So when would I want to use 3D versus 2D? So with 2D, 2D is very good at seeing contrast and print on an object. So if I'm looking at a box of cookies here, I can see, and I want to analyze what's actually on this box. Looking at the 2D image is going to let me do that, because 3D is just going to look totally flat because all the 3D data there is no 3D data, it's a flat box. But if I want to see how many cookies are in each of these slots here, I can take a 2D image and it can be pretty difficult to tell. So maybe I can make that work by saying there's a height difference or there's a size difference between each of those cookies. But that's a hard way to handle that. So if I use my 3D data, I can see that, hey, one of these stacks is actually shorter than the other. So I know that the cookie is missing. So one more comparison here. If I look at a 2D image, and this was an actual application here, where I wanted to be able to tell, hey, is this part right here above or below the rest of this object? With a 2D image, I'm looking at a flat image and I just can't tell. So I just rotate in my 3D and I can say, is this below or above? And I can say, yeah, it looks about to be even with it. So I know I'm okay on this part. So common applications where we see the TriSpector and where it's really excelling right now. Robot picking applications where I need to find the top of the object or the top objects on a stack of objects. Part presence is where the TriSpector is really, really doing well. So in this box of chocolates here, I can tell you that, these 3 chocolates are missing. Looking at electronics, for example, just being able to tell that I have components in the right place and they're at the right height. So I know that they're actually sitting correctly. Missing gaskets is another one. And then robot belt picking, again, is where we're seeing a lot of growth right now with our belt pick device. And then just identifying features that would otherwise be hard to identify due to contrast issues. So this is just specs. I'm going to kind of skip through it again. We can just see that depending on the size of our device, we have a different field of view and our things like resolution changes.
Hey, Sean, this is Jim Staniszewski. Hey,
yeah.
We had a question about the resolution.
Yeah.
And I think that slide you just had up was showing it pretty good. I think you had it circled.
Yep.
In the middle there, the height resolution depends on which model you choose.
Correct.
I'm sure later we'll go at see the different field of views. And then the 3D profile resolution is kind of the, I guess, the Y dimension, not the Z dimension. That's across the laser line.
Yes, that would be our X dimension, the profile resolution. So that would be, if I'm looking at, let me go back to that slide here. So the profile resolution would be this direction across the board.
Right.
And then height resolution is up and down. And then Y resolution is the direction of motion.
Okay, there you go, yeah.
Yep, and it's a little backwards from, I don't want to say backwards, but in a normal 2D application, your Y direction would be, up, and your X direction is being across the sensor. And so it might not necessarily line up with how we're talking about it in our.
Yeah, and there's another question from Jason about the tools that are kind of like the position compensation. I think you're probably getting into that later, but the answer is yes to that too.
What do you mean by position composition?
Well, we can correct. So the question was how to correct for like pitch and roll and movements of the object versus like the taught object. And yeah, that's part of the actual programming.
Yep, yeah, and I'll show that tool in a sec, because that's actually what I'm going to get into after this next slide here.
Great, thank you.
So this is just kind of a breakout of, hey, what goes into a TriSpector application. So typically we're using an encoder. I will say for this configurable TriSpector, we don't necessarily need an encoder, but it certainly does help to have it. Power IO, just for maybe sending a trigger signal to our device, or we can have the option to just output data, and then also output digital IO signals, and then our Ethernet cable for configuring the device and sending data out of the device. So real quick, I just wanted to mention that we have this belt pick device. The benefit of the belt pick is it's very easy to use. So I don't have much experience with robots, and in with a UR robot, it took me about 30 minutes to get the belt pick set up and picking objects off of a belt. So it's very easy to use, goes directly to your robot controller, and then you just basically get going from there. So I want to mention that we have it. Anywhere you might be using like Delta robots is a good place, good idea to think about the belt pick. And again, the reason this 3D belt picking is beneficial versus maybe a 2D system, one is it's continuous. So there's no need to stop the conveyor system. It just always is taking its images, and there's no gaps. So we always get every object that comes through, and then it's contrast independent. So if I have black objects on a black belt, I can tell you that, and I can also give you the height data. So if I have something like a bag where I don't accidentally want to pop the bag as I go to grab it, or let's say if you search the sick belt pick, we have a image or we have a video of Oreos on YouTube. If I have two Oreos stacked on top of each other, I can tell you that they're stacked on top of each other, and I can give you the top point. So if you want to pick that Oreo off and move it to a different spot, you know that, or if you simply don't want to pick it, we can give you that information as well. So I don't want to bore you too much with PowerPoints. I could certainly keep going and show you all the tools here. I have it, but I'm just going to show you the actual PowerPoint here, or sorry, the actual device here. I apologize for my messy desktop. I know it gives some people anxiety. So I'm going to do this from scratch. So I have a blank job, and the TriSpector does use a job, so a golden image. There are certainly applications where I don't necessarily need a golden image. I just set up the tools that are going to work for my application, and I go from there. So what I'm going to do is I have my TV remote for my second monitor here, and I'm going to scan this, and I'm going to tell you how many buttons are on it using some of the tools here. And then just to show you, so this is a black object, and I have this nifty little skateboard that looks like this. And I apologize because the background wants to hide it, but it looks like this here. So I'm going to put this black object on the black skateboard. So the first thing I want to do is set up my encoder. Now I know off the top of my head that my encoder is roughly 50 pulses per millimeter. And I can adjust my things like my exposure time. So what I'll do is come in here and see the actual live view from the sensor that shows me my laser line. Get this closer to my field of view here. So I can scroll in and see the laser, and it gives me data about the intensity of the laser coming back, just like I would think of traditionally with 2D cameras. So I'm going to pump this up a little bit because I do know what I need here. And then the other thing I can do is look at the laser threshold. So if I look at this intensity value, and I was going to point at the screen physically like you could see it, I'm going to look at this intensity value down here and say, what is the average intensity over this object? And we're seeing some pretty low numbers here around 50. So I'm going to bump this down to 20. I'm going to come back to my live 3D. We can see I'm looking at my full field of view, and I'm going to take a scan here, forcing a trigger. All right. So I got some data. I can look over the top of it and look around, and I can see that my image is probably a little long because I'm getting a lot of data I don't need. I'm seeing the desk, and I'm seeing the skateboard itself. So I only want to look at the remote. So I'm going to do this, and I'm just going to click and drag so that I'm just above the skateboard so that I can ignore that data, which isn't really useful to me. You can see I'm above the skateboard. And we can see that my box turned red here. So at the bottom of the field of view, this is how wide it is. So I'm just going to shrink it down until it's not red anymore. There we go. So there's a couple of reasons why we want to shrink the field of view. One, I don't want to look at all this data. The second reason is, why would I process and try and process pixels that are never going to have data in them, or especially not useful data. So for that reason, I'm also going to shrink it to 180. So if it were to rotate back and forth, that's okay. And then the big thing here is it is finding edges based on height because it's using the 3D information. So I want to count how many buttons there are on this remote. So I'm going to add a blob tool, simple blob tool here. I'm going to shrink everything down to help my processing time so that I'm only looking at the buttons. So right now I'm finding one very large blob. It's telling me the area is about 6,000. So I definitely want to change some of my settings here. So the first thing I'm going to do is change this so that I'm only looking at, with my tool, just above the base of the remote, so that I'm finding the buttons rather than the actual body of the remote. So if I come and look at it again from the top here, I can see that I'm finding some data in the back. And I can go look at, okay, what is the actual size of these buttons? The average is about 92 square millimeters, and it goes all the way down to 11 millimeters, square millimeters, and that's probably this one right here. So I can set my range to be, I'm going to give it a little extra, and I'm going to say 200 square millimeters. I'm going to say 125 square millimeters to 12 square millimeters here. So if I look at this, I can see across for every one of my buttons, and I can tell you that it's giving me 32 blobs. So there's 32 buttons on this remote, and it's giving me data about the X, Y, and Z position, and it's also giving me data about the area. Now, if we go one step further, so let me take a quick scan of this, and we can see that if my position changes just a little bit, and I grab a new image, I'm still finding the buttons on my remote. So I can see that my first go around, I'm getting some information here that I don't want, and I'm missing 2 buttons. So I'm going to go make some adjustments to my tools. And mainly what I'm going to do is go back to my job here. I'm going to actually add a plane tool. So the plane tool is going to find the back of this remote here. It's going to give me a flat plane. And I'm going to make a couple adjustments so that I'm ignoring the bottom set of data and the very top set of data, just in case I were to have any noise. I'm going to set that to like 85. And then I'm actually going to lift it off of the remote by about 1 millimeter. So now what I'm going to do is I'm going to come to my blob tool, and I'm going to start ignoring data that is below that plane. So what that's going to do for me is I'm going to start ignoring pixels that show up below this plane, which should be at the very top of the remote here. And I'm going to knock this back down to 10 because we were missing those buttons before. And I'm going to try taking another scan and see if that helps fix my issue here. There we go. So now I'm not seeing that data on the edge of the remote anymore, and I'm counting 32 blobs. So I can count all the buttons on my remote, and I can give you the positions. So if one of these, I can triple check that, send this data back to, say, a database here. For each of these blobs, I can give the area, for instance. So sorry, I skipped ahead a little bit here. So let's say that this is all I need to do for this application. I'm going to get all of these blobs, all of these buttons, make sure they're there. And I'm going to do 2 things. So I'm going to come over here, and I actually want to send this to PLC. So let's say I want to send it to an via Ethernet IP, which is built into the device. And I'm going to send the area of each blob out to my PLC so that I know what size each size is, and I can make some assumptions of, if I'm missing one of my larger blobs and I only count 2 blobs above 90 or 1 blob above 90, I know I'm missing one of these buttons, for instance. And then I'm also going to say, I'm going to put this at the front here, my blob count to tell me how many buttons there are. And we'll separate it by a semicolon. So when I take my next image, it's going to give me that data. So that's one option. So I can say my blob count is 32, so I know my buttons there, and I can get the actual area for each one of these. Within this, if I really wanted to, I could also get the center of gravity for the X, Y, and Z position. Not an issue. I can do things to calculate a volume. And I can also come back here, and let's say that I don't want to do, I don't want to use any of the Ethernet results. I can actually just say, I know it should be 32 blobs. So if I have 32 blobs, the tool will pass. I don't have to worry about sending that data out anymore. And I can go over one more step here and look at my interfaces and say that I have my, so these are three of my inputs here. So dedicated trigger input. I'm going to take one of these inputs and change it to an output. Go back to my results and say on a result, do I pass or fail? And I'm going to tell it to stay on for 5 seconds so that we can see it on the screen here. And when this result is okay, I'm going to get a signal telling me that it's okay. Oops, and I failed. So I didn't get a signal because I didn't find the remote correctly for some reason here. Looks like I have some bad data. Let's try this one more time. There we go. So my result is on. I'm getting a digital output, as well as if I needed to, getting an Ethernet string telling me how many blobs there are. So like I said, Ethernet IP is built directly into this, so we don't even need to set anything up on this side. And we have some documentation, but we can also send commands via Ethernet TCP IP or Ethernet IP. We do have the option of sending things to an FTP server for saving images. And then we have an option for an SD card as well that we can slot in here and save images there. So that is what I have for you. I see that there's a few questions in the chat here. So I'm going to open it up for questions.
Yeah, a few questions came in, Sean. One from Dave Gamble. He's asking, are you able to detect orientation of a blob? For example, can you detect that the button is rotated 45 degrees?
Sort of. So rotation of a blob, we can do calculate the angle here. So yes, as long as, you know, I have some of these as, you know, this is a circle. So I can't, you know, it's a circle. So rotation isn't as useful versus, you know, this is a rectangle. I can tell you that rotation. And again, that's something we can come over here and we could output our blob angle now. So yes, we can, okay. I should say.
Thank you.
Depending on the shape.
And Jason had another question. He says, I think you might have already answered that actually. He says, does Ethernet IO support Ethernet IP, implicit IO instead of TCP IP strings?
Yes.
Okay.
Yep. So that's built in. It's no need for any intermediary device. It's coming directly out. And we have some documentation on that that we would always send you if that's the method you want to go with.
Okay, and I think to piggyback his previous question, it says, is there a tool that can correct for roll and pitch with reference to a datum plane for the Z measurements? I think you touched on that.
Yeah, so we would generally, so let's say, you know, I want to capture my belt. We'd put this plane tool onto the belt. And then we'd have to do some calculations to say when I capture these images or capture these objects here, that I have that roll, and I'm not necessarily looking straight from the top down.
But Sean, you could also find that, like you could find the controller and then adjust your blob tool in order to look only in the area that the controller is oriented. You know what I mean? So if it's not coming down perfectly straight every time,
Oh, I see what you're saying. So
Yeah.
I'll take an image here. I don't think it's going to work because I'm not quite far enough away for the field of view to capture it, the whole remote. But you're talking about the remote coming down like this.
Right.
And yeah, yep. So the shape tool is making that adjustment, and it's going to find. So looks like I just barely caught everything, but so the shape tool is finding these edges on the unique shape, and so it is actually rotating all of the whole tool set, our blob tool and everything, with the image, even though it's placed differently in our field of view. The caveat to that is if it's not a unique shape, so if it is a circle, and there's no height differences within that circle. So if I were to just cut this off here, and I can't find any height differences here, that we're going to have to do some other tricks to get our tools to find what you're looking for. Circles in general and object locators, it's a circle, so if it's not a unique shape, finding orientation can be tricky, where this object is a unique shape and it's working and finding the orientation of the object.
Okay, thanks. I think another question came in from, let's see, Spaz to everyone. Can the TriSpector detect different colors, or is it working based on part geometry?
So it is working on height differences. So let me do this a little bit here. So it's not contrast based. We can obviously see that there's different contrast here. We have one tool for making an inspection based on those intensity values, and it's looking at this area here. And I can look at this intensity range, and let's say I only want to find white pixels, which is the white on this remote here. And we can see that I can very clearly tell that this white text is here versus the black. And I guess we're seeing the text on these buttons as well. I don't have my camera on, but we're seeing the text on these buttons, and the red button is showing up as white, just because red laser, if reflecting off of a red object, is going to reflect with a higher intensity. So generally, we're looking at, for all the other tools, we're looking at height differences, and that's what we care about. But we do have this one intensity value tool. Now, in some of our other products, and even the TriSpector P, where it's programmable, I can use that, and I have a few more options to program into my application contrast and intensity tools to inspect other features. But that would be, again, not this configurable device, one of our more advanced devices.
So really, I think the answer is yes and no. I mean, it's not color based, but contrast. So it's more like a grayscale type of camera.
Yeah, it is.
Regard.
Yep, it's yes and no. It is. Technically, we can do some, but it's not looking at is this red or blue. It's looking at the contrast from the grayscale value we get back based on the intensity of the laser.
All right, I'm looking. I don't see any other questions come in. Let me give it a minute here. Oh, a few more came in.
Yep, I see the one from Andrew Kern. Will reflection play a role? So for some shiny objects, and actually a really good example is objects wrapped in shrink wrap. Shrink wrap, we can get some reflections, and let me see if I can throw something shiny on here. I'll just kind of show it like this. So if I look at my sensor view, this is a nail that I just threw on from that I had laying around for some reason. I don't know what it came from. But if I have a nail here and it were making reflections, we have a couple things we can do. So if we have very shiny objects, we can actually determine which laser peak we're going to look at. So we can see here, I have my laser here, and if there were some laser data underneath, and this is an instance of looking through a bag, a clear bag, or some shrink wrap, I can just say I'm going to look at the very bottommost, and that's how we generally look at eliminating some of that noise. If it gets very, very complicated, again, we can get into one of the more advanced cameras and do some more filtering in that aspect. So I can see with the nail here, and it was in a wall, so it's got some stuff on the end of it here, but we can see the nail on top of the remote. So if I have foreign objects on top of what I'm looking for, I can tell you that as well. And then I see a question from Jason Schwartz. Can I provide list price? I would work with All Control. I like to separate myself from the sales side and stay away from numbers if all possible. Yeah, just work with Sydney and Jim at All Control, and they can get you some pricing information on this.
Yeah, you can reach out definitely to All Control, your sales rep, or myself. We can definitely work with you on pricing on any specific application that you might have as well.
Yeah, maybe this is Jim. One thing I'd like to add, I mean, so this is different than what a lot of you have hopefully seen, you know, with 2D cameras. It can solve a lot of the applications where you don't necessarily need to see that contrast difference or reflectivity difference. But it's not, TriSpector is meant to be in more like SICK loves to call a 3D vision sensor instead of a full vision system. So we're not talking about something that's going to be in the $15,000 to $50,000 range. I think a ballpark price on this guy, just off the top of our head here, is probably between $7,000 and $8,000. So it's meant to be a problem solver, something that can solve some maybe applications where you have a 2D camera that you're having trouble with. I can bring up one application where we were detecting clear glass bottles in a box where our customer had to build up a whole cell and spend a ton of money on lighting for a 2D application and still had trouble with it. We popped one of these TriSpectors in there. It wasn't the simplest application, but we got it to work really robustly in a short period of time without adding a big shroud or expensive lighting, things like that. I think one point, I don't know if Sean brought up, but we didn't talk about adding any light to this. So in this application right here, we have the laser line, and then the imager is tuned to that laser line. So we don't have to worry all the time or usually about ambient lighting or shop floor lighting or adding different lighting to bring things out. So I think that's one thing to take away from this is 2D vision always seems so simple, but in the end, you need to make sure that your object is lit up well. So a lot of times you think, oh, I'm going to use a camera with a simple ring light, and then you're not getting the image you need. So you have to end up adding, you know, thousands of dollars or more lighting to get it to work properly. Whereas for most applications, for a sensor like this TriSpector, there's no external equipment. I mean, you got the camera, probably an encoder, and that's about it, and the cables. So that's kind of the main takeaway, I think, from this, is that it can solve a lot of applications that either have been very difficult or sometimes impossible with a 2D or a standard type of vision system you might be used to. So unless there's any more questions, maybe we should wrap this up so that everybody can get back to all the stuff you have to get to today. Thanks a lot. I mean, this was great with all the kind of back and forth and the questions, and thanks to Sean for putting together this demo. But yeah, if you have any questions or want to see a demo, I mean, about 5 feet away from me, I have the TriSpector here that we could bring out to your location. We can take some of your parts and get images. You know, we can do pretty much whatever we need to do to show you this product. So if you want to see a demo, if you have some kind of application you're looking at, please reach out to us or to your All Control sales rep, and we'll definitely get it going as quick as we can.